Hello everyone, am I audible?
Yes, you audible.
Uh, so okay, so let's start the session now. Today we will be covering the week three theory, and in the tomorrow session, we'll follow it by the implementation of the TNN. Okay. So before starting, yesterday was the deadline for the week one GA. Uh, Anybody has any doubt in that part? In any of the question in week one? Yes, Atul.
Yes, sir.
Yeah.
So, so I'm thinking about how it beat the 24.
Sorry, your voice is very low. I'm not able to hear you.
Sir, in question 24, there everywhere is mentioned the import, but in question number, especially in question number 7, there is no mention of import torch. So all the code that is pasted there is already got going to give error. So there is no means of giving 24. So how it give the 24 as answer?
Yeah, I saw that query on the discourse. I will forward that to the instructor, okay? They will take the final decision what they have to do, okay? But the answer that is given is assuming that all the imports are there, and with that we are doing.
Okay, but sir, you are mentioning import everywhere, but not just a single question you have left there. So it
Yeah,
is
yeah,
practically imagine that there is no import, or you are giving five options. One is error, or other is 24. So it's
mhm.
very confusing.
Okay, okay. I will forward that issue to the instructor, don't worry, okay? They will take the final decision. Yes, Shubham?
Yes, basically I have a problem in the week two. That we started like 1 week ago. Sir has taken the like the practical session. So I want to
Mm-hmm.
ask that what things I need to remember for the coding part. Like what do I need to practice because there are a lot of things over there.
Mm-hmm.
So what do I specifically need to practice because like I need to do certain filtering things out over that all the topics.
The main thing that you should know is if you want to create any custom network for on, then how you will create that. You'll first initialize a class, okay, and that you will set up the initialization function, okay, and that you will define what kind of layers, okay, you want to take. Then you will define one forward function in which you will define how the feed forward part will go for that network. Okay, that step you should know how you will define that. Okay, and for that step, of course, you should know how you are going to use the layers that you have, like linear layer, or now we are going to study more layers like convolution, max pooling layer, etc. And some basic operations like min, max, etc.
Okay, okay, sir. Okay, sir. Thanks.
Yes, one minute. So, Gaurang, what's your query?
So, like question two for week one,
Hmm.
why is it, why, like, can a data set represent XOR and XNOR at the same time?
See, it depends upon how you are taking the symbols here. Okay, whether you are going to take the positive one and 0. Okay, that's the main confusion with this question. Okay, uh, don't worry, we have already forwarded this issue to the instructor. Okay, most likely the last option for this question will be excluded from the grading part. Okay.
So, like, let's say, like, further on, like, for the later weeks, let's say, uh, does it represent XOR or does it not?
See, for the XOR, how we represent the XOR, that if you have a different sign, then it will be the 1. And if you have the same values, then it will be 0. Okay. So if any function follows that fashion, then we will call it as XOR. Okay, the main confusion comes whether you are going to take +1 as the 1 or -1 as the 1. Okay.
Yeah, so let's say like we are using non-conventional labels, like in the question -1 or +1.
Mhm.
Then like it's not 0 or 1.
Yeah, they have supposed to given one line also what here +1 will represent and what -1 will represent. Okay, that's the one thing that
Okay.
is missing in the options. Okay.
Yes, that was my confusion. Thank you.
Yes, Anshuman.
Yeah, I have a small doubt in question number 12. Exactly, I am not able to grasp the question. How
Uh,
it does not give an error.
okay, why do you think it will give an error?
Because the shapes are not matching. I tried to study the broadcasting thing, but I was unable to understand it properly. So, could you just
Yeah, so the
give a brief
broadcasting rule
explanation?
is so in that question, if you see we have one matrix A, okay, that is defined as a 3 cross 4 matrix, okay, and then basically 3 cross 4 tensor we are using, and when we are using a 4 one dimensional tensor which has 4 elements, okay.
Okay,
Now, what we are doing in the end is we are doing this strict B. Okay. Now, it will not be as multiplied as like your matrix vector multiplication. Now, this will be multiplied as element wise. Okay. But what happens in this case now that yeah, broadcasting rule will apply. Okay. That will be applied by the PyTorch itself. Okay.
okay.
And after that, it will flatten this output. So it will look like that's 3 cross 4 matrix. Okay.
Uh, yeah, okay,
So
fine.
each of these,
So,
yeah,
how is 3 cross 4 multiplied with 3 cross 4 matrix?
it's the
I,
element wise. See, that's why I said like here, this symbol, that asterisk symbol that is given here, okay, it's not the matrix multiplication symbol. For the matrix multiplication, you use this at the red symbol. Okay, this symbol is
okay,
for the element wise multiplication. That means
okay,
if you have a matrix A equal to 1, 2, 3, 4, B equal to 5, 6, 7, 8. Okay, the multiplication will happen element wise. One will multiply with 5, 2 with 6.
all right, got it.
Okay.
So this notation is used in the like the coding part, right?
Yeah, coding part.
Yeah. Okay. Okay.
It
Understood.
was a
Understood.
coding question. The same convention is follows in the NumPy also. Yeah. Any more query? Okay. So let's start the session for the week 3. Mm. Let's recap whatever happened so far. So we started with why we need to switch from the traditional methods to the uh, deep learning methods, deep learning neural networks. You set the baseline for that. And then we saw different kind of network that come up during that time, starting with the MP neuron. Then we saw the perceptron model, then the MLP or the feed forward neural network, or basically call it as artificial neural networks. Okay. So we have seen so far, okay, how you do the forward propagation in that and how you do the backward propagation in that. We have also seen the implementation of the artificial neural network and the simple linear regression model in the PyTorch. Okay. Now, for week 3 and week 4 onwards, we will be moving to the vision part or the computer vision part, in which we'll be dealing with uh, unstructured data, and specifically we will be having the images. How you deal with images that you have. Okay. So first of all, a little background on the image part. So on the screen that you can see is a grayscale image. Okay. Now a grayscale image is a one channel image. Okay. So we can have multiple channels, just like you have an RGB image, which can have 3 channels. A grayscale image will have one channel. Okay. So this image here is a one channel image and it will have some dimensions. So let's suppose 20 cross 100. Okay. So it's an image of 1 cross 20 cross 100. Okay. Now throughout the course, this is how we are going to represent the dimension of an image. It will be in the form of C cross W cross H. Okay. Where C represents the channels that you have. Okay. Or you can call it as the depth of the image. Okay. W and H are the width and height of the image. Okay. And that image for our vector matrix representation form, yes, Shubham?
So what do you mean by channels?
Channels, as I said, it's like in depth of the image. So for an RGB image, you will have three channels: the red one, the green one, the blue one. Okay. As it is a grayscale image, it has only one channel. Okay. So channel is similar to your depth of the image. Okay. Now for a grayscale image, you can think of it as like a matrix, okay, which will have elements from 0 to 255, total 256 element it can have. Okay, so each of these value will be between 0 to 255. Okay, and this is how a general pixel values for a grayscale image will look like. Okay. Now, the types of image that we are going to see in our course are the most left-hand side, that's the binary image. Okay. It has only values either 0 or 1. Okay. So 0 for the black and 1 for the white. The second image that you have is the grayscale image that we have seen above. Okay. And third one is the RGB image, which has 3-channel color. Okay. Now a general overview of the RGB image. If it is of shape 224 cross 224, here 224 224 represents the width and height of the image. Okay. The proportion of image or a general dimension in the width and height. And the 3 channels that you are going to have, the red, green, and blue. Okay. So think of them like you have a 224 cross 224 dimension. Yes, Karthika.
This width represent row or width represent column?
You can take the width as the row.
Width is row and then height is column, is it?
Yeah.
Oh, thank you. Thank you.
Okay.
So at max it will consist of 24 pixels. 224.
Not 224 pixel. Each of these value again will be between 0 to 255 values. Okay. So the 224 is not the number of pixel it has. Okay. 224 is the width or the height of the image. Okay. If you
Yes.
look at your any phone that you have captured any photo, okay, in the details of the photo, it will also show you the dimension of the image. Okay. What's the width and height of this image. And of course, if you want, you can basically bring any image that you have into a particular dimension, okay, by squeezing it or cropping it. Okay. And this was about how you take an RGB image. So it will have a red channel image, a green channel, and the blue channel images. Okay. So kind of like you have 3 feature maps. Okay, the red one, green one, and blue one, and they are stacked together. So that's why it has a depth of 3. Okay. The channels here are 3. Now you can have more than 3 channels also, but I don't think so. We are going to deal with such kind of images in our course. But such images also exist in which you have more channels than 3. Okay.
So like that, the 4K and the HD quality comes with more channels.
No, but yeah, you will have different tasks for that.
Okay.
Yeah.
So on the left side in previous slide, left image, not this one, sir, after this one. Next slide.
This
So this one on left side, is this RGB or grayscale?
this is an RGB image. This is the original image that you have. Okay. You can extract the red channel, green channel, blue channel image from this. Okay. And that's what I extracted here from this image.
More channel means what? Okay.
The more depth will be there. Okay. Currently, the depth or the channels are 3. You can have 10 channels images also.
Oh, what are all the? Because RGB we should get all the colors, right? That's what.
Yeah, but you can have more
basic,
channels also. That some different images that we will not be dealing with in our course.
Oh, okay. Say for
I will-
maybe some kind of a 3D or. Okay, we are not dealing it. Okay. Okay.
Yeah. I just said I was telling that these images also exist in which we can have more channels. Okay.
So mainly we have these three colors, right? RGB. Even if we have like more, then probably it will be combination of
Yes, yes,
either of these.
combination. Now, what are the tasks that you can do on images or using images? What are the tasks that you can do? So,
We can identify things.
yeah, so that's like an
Uh,
object detection.
We can
you can
identify events. We can identify things.
You can identify
Image
faces
captioning.
like a phone.
Image captioning will be a different task. Okay, that cannot be done just using the CNN network. So,
Okay, sir.
yeah, image
OCR.
captioning is also one task, but it's just that it will require more complex structure. Okay, anything else?
Sir,
Classification.
OCR.
see generating image, I think.
Okay, generating image. That part something that will come later. Okay, you can simply do the classification also, image classification, like classifying the image whether it's an image of dog or cat. Okay, and
So that's detection only, right?
not the detection. Object detection is basically what kind of different object that you have in the image.
Okay,
Okay,
okay.
and there's something more advanced in this, like object recognition. So you recognize all the objects that are there. So we mentioned where the grass is, where the sky is. Okay, so all the things you can highlight in your image. Okay.
Sir, what about OCR? Optical character recognition. I mean, where we extract text from the image.
Yeah, that part also you can take, but I don't think so. That part also we can done along with the CNN. So yeah, mainly the object detection, image classification. Okay. Uh, Furthermore, you can look at like object recognition and the cementing segmentation. Okay, but yeah, mainly we will be dealing with image classification, and that's what we'll be seeing in the implementation part, where we'll build a convolution neural network for our fashion MNIST data set. Okay, in which we will be having 10 classes. Okay, 10 different type of clothes that you have, and we will try to classify each of these images. Okay, we did this same experiment using MLP also in the week 2, and the same experiment we are going to do with the same data set now with convolution neural network. So before that, uh, what's the problem with the MLP for the vision task? Why can't we just use the MLP, and why we have to move with other neural network structure? Yeah. Anybody knows?
So like the features would be done, like the feature engineering would be done better in this ANN than the MLP, like the usual ML models.
Should be the
Uh,
same
Sir, because of
advantage.
unstructured
ML,
data.
yeah, okay, and structured data. See, for the MLP and NN, you can take them as the same. It's just that MLP only be considered as one hidden layer, ANN is just can stack more hidden layers. So either you can choose them. If we are talking about MLP and NN, you can take them interchangeably. Okay. The question here is, if we just use the artificial neural network structure that we have, what's the problem with that for the image classification case? The first problem arises basically the number of parameters. Okay. So image are basically high dimensional object. Okay. Even if I like take an example of the above case where we have a RGB image of 3 cross 20 224 cross 224. Okay. 4 cross 2224. Okay. what you are going to do if you are going to train a simple neural network case, you are going to flatten this image, okay, and take it as a 1D vector. So in that vector, how many elements will be there? It's just whatever you will get the product of this.
So what is 3 here?
3 here define the number of channels that you have. Okay, as this image has 3 channels, red, green, and blue. So that's the 3.
Okay.
Okay, the later part is the width and height. Okay, in the case when you are going to train a simple ANN network, you have to flatten this image. Okay, to make it a 1D vector. So whatever the product that will comes out from this, okay, result, that will be the dimension for your input vector in the artificial neural network. Okay, and you can see that it's very high number. Now, if you are going to then again use some hidden layers with some, let's say 128 or 256 number of neurons, and the number of parameters quickly blow up to very high value. Okay, so it will take very high computation cost to train the artificial neural network in that case. Okay, so one of the major issue is the number of parameters that you have. Okay,
Really, we need to take this 3 into 224 into 224. Why not 3 into 224 only?
why? See, you have to
No,
capture
no.
the width and height both, no? Your input image is, of course, in
224
this
by
dimension.
224 is okay. 3 is
So
required.
yeah, 3 is also required. Even if you take the grayscale image, and still it is like 224 cross 224. Okay. And if you are thinking about that, we can crop the image and then like
It looks
shorten
the
the width
same.
and
It looks almost the same. The image looks the same. Only thing the color changes.
yeah, the color changes. Okay, you can take the grayscale image also. In that case, also, you can have the dimension like 100 cross 200. Okay. This itself will give you 20,000 input dimension vector. Okay. And in the case, if you are going to take the like try to reduce the dimension of the image, then in that case you are going to lose more information.
Okay, for information and then okay, how it mixes, you need the color also. Okay. Okay.
Okay. So the number of parameters is one major issue. The another is the way the artificial neural network work. Okay. Yes, Satya.
In the case of, let's say we are categorize some letter and the letter is written in red color. In that case, how will be the data processing? And, I mean,
Sorry, can you repeat?
so let's say we are, classifying some letters and the letter is in color and that is in red.
Okay.
So in that case, what will be the data processing like?
Okay, so you are saying you have an image and your task is to.
Let's say it's a color image, 3 channels. So in that, a letter is written in red. So it's only, it will be appear only in the red channel, right? Or it depends on
No,
the background also.
it will appear in the all the channels.
Yeah,
okay. It's just that it
the
will get more
background, yeah.
highlighted. It will get more highlighted in the red one, okay, rather than the blue and the green one.
Okay, so the data processing will be same, or we
take the same data processing for each of our inputs.
okay.
Yeah. So I hope the first point is clear, the number of parameters issue. The second point is the destruction of the special feature. So by that we mean the structure of the image. Okay. So because you flatten the image input, okay, initially, you are going to destruct its special feature, that's like the position where these things are represented. Okay. So for example, in this image, this is where the leaf is represented. Okay. What is the position of the position of the leaf in this image? Now, where when you are going to flatten it. Okay. So let me take some example. Okay. what will happen in the case of flattening? Everything will come into one line. Okay. So the position factor for this leaf, okay, that will get destroyed because you are changing the structure.
Same like printer, right? How printer prints. It prints a line by
Yeah.
line, the same image.
So everything will come in the
That's
straight.
what you mean by flattening, right?
Yeah, flattening. Everything will come in one dimensional vector. So it's a 3
So
cross 3
basically, instead of second line, the second line will be appended or
at the
will be a continuation of the first line. The third
yeah,
line will be a continuation of second line,
there
like
will be
that.
no
Yeah.
second or third line. There will be only one
No,
line.
no. I'm just assuming a printer printing, right?
Yeah, sure.
Or your
So,
rows.
so
Whatever
my
rows.
understanding on flattening is that, like, in case we are flattening this image, then the depth and all those things which are shown in this image would be neutralized. Is it the same, or like
What do you mean by here neutralized?
means like in image something is looking at the background, something is looking like in forward ground. So, but when we would be flattening those things, it would be on the same scale, on the same plane.
Yeah.
Although still it is on the same plane, but
Yeah,
in
of course.
image it is showing that something kind of thing.
Yeah, you can think of it like that. Okay. And that's the reason why those particular positional feature, the special feature that we call it, okay, that will get lost because you are changing the structure. Okay. So that is one of the.
Currently, flattening means I'll be having 3 into 224 into 224 features, right?
Yes, correct.
That many features will be. Currently,
Yeah.
it was having 3 initially, 3 channels.
No.
Now into
3 channels.
224 into 224.
So
this many features will be there, and then
still you have. Okay. See, once you flatten it, then you will be having a vector which will be in this dimension. Still, what will happen in that case is if you are going to train the MLP, okay, then your number of parameters will blow up. Okay, because of this high dimensional input feature. Still, you will be having the same amount of features because still you have the 3 into 224 into 224 images. Okay, but the way now we are going to train the images will be in some different way instead of the MLP way, because in the MLP way the number of parameters will going to blow up. That's our main concern, because with that many high number of parameters we need more computation power, and sometimes it's not even feasible to do the computation. Okay. Yes, Shubham.
So like in the normal CNN networks, we will here also do the flattening things. The CNN
No.
part also.
CNN works in different way. CNN does not need or require you to flatten the images. That's
So
the
like
main
you
power.
have told, so just move the above slide. Yes, this one under the image you have given a matrix like 1, 2, 3, 4, 5, 6, 7, 8, and done the yes, this part. This is a flattening part.
This is the flattening part that will happen in the ANN case.
Okay, artificial neural networks. Okay.
We have not started the CNN part yet. Till now, I am just explaining what is the problem with MLP or the ANN. Why can't you use the ANN on the images? You can use it, but
so like MLP also follows the ANN. That's why you are talking about that it will flatten the image, right?
Yeah.
Okay, fine.
Okay. Yes, Chandra.
Sir, I did not understand why we have changed the structure to flatten structure.
Because that's how your artificial neural network get trained. In that, you take the input as the 1D vector.
So it is only due to the input constraint that input layer needs a flattened structure. We have to change it to a flattened structure.
Yeah. That's how your artificial neural network structure is defined. Okay. Its architecture is that it will contain a 1D dimensional vector, and that you will feed it into a neural network, and then you will get the output. Okay. It cannot take image as its own structure like a 3 cross 224 cross 224 dimensional object directly. You have to flatten it first, only then it can take.
So, sir, any network which can take this unflattened matrix as an input?
Yeah, CNN takes.
CNN takes this matrix structure.
Yeah, without flattening it. We direct do the operation on this image.
So, sir, in terms of, let's say, training, both the networks can give good performance. It is not that.
No, CNN works really good on the images compared to the artificial neural network.
So then why we are unnecessarily flattening and training ANN then?
We will not do it. It is just that I'm telling that why we need to move to a different neural network now, because the NN does not gives very good performance on the images. Okay.
Oh, okay, sir.
We won't be training ANN on the images. It's just that I was mentioning the cons of using ANN on the images. Okay.
Okay, sir.
Yeah. So these are the main things. That's why we cannot use artificial neural network or the MLP on the images. Okay. You can use it, but of course there will be certain problems with regards to how you will get the accuracy or the performance of the model and the generalization and the number of parameters for the computation power. So we need a better neural network structure to capture this. Okay. That's where the CNN comes. That's the convolution neural network. Okay. Now this is the architecture. Now this might look horrible to see in the starting part. Don't worry, we will unpack all the layers that it has. Okay. So I'll come back to the structure a little later once I will explain all the layers that it has. Okay. So the layers and the terminologies that we are going to study now. So it has a convolution layer. I will describe now what is the convolution, don't worry. The pooling layer and the fully connected layer. Okay, about the terminologies that we are going to use. The kernel or the filter. Kernel and filter both can be used interchangeably. Okay, so both will represent here the same thing. The stride and the padding. Okay, so just bear with me for a few minutes and then you will be able to understand what are all these things. Okay, so I will explain the 1D convolution here. For the 2D convolution, I will use the different slides, okay, which are made by Karthik sir. Yeah, so 1D convolution. So for the 1D convolution, it's very simple. Suppose you have a 1D input, 1, 2, 3, 4. Okay, think of it just like an row, 1, 2, 3, 4. Now, I have some weight parameters with me. Let's say 1 and 1. Okay, so this is like your filter or your weight matrix. Think of it like that. Okay. Now, how the convolution operation happens, you will take this filter and put it at the starting point of this input 1D convolution. Okay. So this is my input and I will place this my filter 1, 1 on the top of it. So because it is a two-dimensional weight row vector, okay, it will only cover this part, right? And wherever it is fitting in that piece, okay, I will multiply those elements. So that means I will put this filter here. So that's why this 1 will be multiplied with this 1. This 1 will be multiplied with this 2. Okay, so I will do this element wise multiplication. 1 into 1 and this 1 into 2. Okay, and then after doing all the element wise multiplication, I will add those results. Okay, and I will get some result and I will store that in some other vector or matrix. Okay, so this is 3. So this was the result that I got if I put my filter here. Okay, we'll start from the most leftmost hand. Okay, and now I'm going to slide this filter across this input. Okay, so first position was here. The next position will be from here to here. Okay, again because it is a two-dimensional vector. And again we are going to do the same thing. We will do this element-wise multiplication. This 2 will now be multiplied with this one, and this 3 will be multiplied with this one. Okay. After doing the multiplication, I will do addition. I will get 5. Okay. 2 into 1, or maybe same. 1 into 2 plus 1 into 3, 5. Next, I'm going to again slide it. So we were till here. Now we will come here. Again, we are going to do the same thing, element-wise multiplication followed by addition. 7. Okay. That's your convolution operation. Okay. You are going to place your filter or your weight matrix or kernel. Okay. These three terms will be the same in the case of CNN. Okay. Place it at the leftmost side of your input, left and the top if you go into more height also. Okay. Then you are going to slide this. And in each part where you are placing it, you will do the element-wise multiplication followed by the addition. And that output you will store in some other vector or the matrix. Okay. Yes, Shubham.
So like you have told that you will slide through the thing, like that upper part is the input area, right? That 1, 2, 3, 4.
Yes, this is input.
And the below is the weight vector.
Yes.
So you're just multiplying the things and adding, like element wise you are multiplying and adding the things, and you are treating that as a convolution, right?
Yeah, this is the convolution operation that we are doing now. Okay, this applying filter on this image and the sliding part and those, the entire thing is called as the convolution operation. Okay.
Yes, yes.
And that convolution operation is generally represented by is I is my input. Okay, W is my 1 minute just. W is my filter or the kernel. It's represented using this asterisk. Yeah. Any doubt in the 1D part?
Sir, can you please
Can I please
explain again convolution operation?
Yeah. So this is your input. Okay. This is your filter that you want to apply. So what we are going to do, we start with that top leftmost part. We'll place our filter on our input. And because it is a two-dimensional filter, okay, that's why it's only able to cover this much. If it would have been a three-dimensional, then it will cover till this. Okay. Now, because it was a two-dimensional, it will only cover this part. Okay. In that, we will multiply these elements. Element-wise, we will do the multiplication. Okay. 1 will multiply with 1, 2 will multiply with 2. Sorry, 2 will multiply with this one. Okay. After that, we are going to just add these and we'll get one scalar value that we are going to put it in some other vector matrix. That's like your output vector or the matrix. Okay.
Okay, sir, and then how do we decide this filter?
That's your parameters that you have to learn. So yeah, how the filter matrix is chosen. Okay, we'll come back to these parts. Don't worry. For now, just understand the convolution operation. Later part, like how you decide it and all. What's the effect of it happens? We'll see it later. First of all, is the operation clear?
Yes, sir, it's clear now. Thank you.
Yeah, we will come to this part also, whether it is reducing the quality of the image or what's happening to the shape size and all. We'll come that part later. Okay. So still, if you see, we have only touched these two parts, the convolution and the kernel and the filter. In the convolution also, we just touched upon the 1D convolution. Now here, one more point I want to out that we did a 1D convolution because your input is in 1D and your filter is also in 1D. What about the output? It is also a 1D. 1D means a 1D tensor. Okay. Now in the 2D, of course, you will be having a 2D image, okay, in which you will be applying a 2D filter, so like a matrix.
How do you say this filter is
1D? Filter is 1D in the sense of its dimension.
2, right? 2.
Yeah, in the R2. Okay. If you go in the functional part of the PyTorch, where we define the dimension, it's a vector. Okay. So that's why the vectors are called as the 1D tensors.
You say 1D, okay, there they have, if it is a point, it is 0. They have 0 also.
Yeah.
Yes.
So 2 means it's 1 for the PyTorch.
Yeah.
So with that reference you are telling.
Yes.
So basically it's in real term, it is 2D. For PyTorch, it is 1D. Is it?
You can take, but it's a one time.
It's x comma y right here.
Yeah. In that sense, you can take.
Okay. So that disclaimer should
Yeah,
be
but
there.
yeah. Okay, so then I will use the terminology as a tensor. It's just that most of you are not familiar with like
Maybe only in the tensor, because for us we have x comma y. So
Okay.
normally in real life it is a 2D. So for PyTorch there it is a different notation.
Yeah.
Okay, thank you.
Okay. Yeah. So now we did a 1D tensor convolution here, and we get the output also as a 1D tensor. Okay. Okay. Now we are going to move with 2D part. Okay. So let's check.
I think you were starting with some point for 1D convolution itself.
Yeah, 1D convolution. I was just pointing out the fact that we did a 1D convolution and we got the output also as 1D.
Okay. Okay. You are talking about the dimension only.
Yeah, output. Yeah, the output
Okay.
dimension.
Okay.
Okay. I'll start with the 2D part. So consider this as your image and this is a filter. Now both are 2D tensor. Okay, both you will have matrix. So we have the height and width of the image, and this F here represents your size of filter. Generally we take with the square filter, but you can take the rectangular filter also. There's no restriction. But the general trend is we take with a square filter only. Okay. And the general trend is also that we take the image input also as the square. If it is not square, we can make it square also. Okay. Now, the same thing that we were doing it in the 1D case, same thing we will be doing in the 2D case also. Okay. The right side here represents the output. Okay. This was your image. You have placed your 3x3 filter on the top leftmost side. Okay. Whatever the elements are beneath this filter, you will multiply those elements with your weight elements that were there in your filter. Okay. Add it. Whatever output you will get, that will come here. Okay. And then you will keep sliding it. Okay. And that's how the 2D convolution will work. Yes, Shubham.
So like I want to ask another question, that how do you like make this a 2D problem like this one that you are showing? I want to ask that only.
How do I make it as a 2D problem? Like
Like how do you represent this as a 2D form? You have told us that you will be starting with the 2D part. This is a 2D part,
yeah,
right?
yes, it's the 2D because it's a two-dimensional tensor.
Tensor.
It's a matrix, right?
Oh,
And your
tensor, right?
yeah, your kernel is
Okay.
also a two-dimensional tensor because it's a matrix now.
Yeah, so understood. Yeah.
Yes, Mona Lisa.
How do you show the convolutional operation and we are getting an output. The right hand side smaller matrix is
Yes,
the output.
yes,
So how do you decide that it will come a 3x3
Yes.
only like this image?
yes. We will come to that part soon.
Okay.
Okay.
Yeah, thank you.
Any more doubts?
Hello, sir.
Yes.
Yeah, could you repeat the how you are multiplying?
Yeah. So see, just like we did in the 1D case, okay, you will place your filter in the top left most side of your image, okay, and then there will be elements that are beneath this filter in the image, right? We'll take those elements and multiply it element wise with the elements that were there in your filter. Okay, I have one algebraic expression for that in the last part of the slide. Okay, there I think it will be more clear how you do it. Okay, but whatever the elements that are there beneath this filter position, we'll take those elements, multiply it element wise with the elements that are there in your filter. After doing that multiplication, just add those elements. You will get one single value. That will be the output value here.
Okay, sir.
You will just keep sliding it and you will get. Okay. Now we comes to the part where you have a three-dimensional image. Okay. That is, you have the depth also now. Okay. And you have kernel that is also in 3D. Okay. So again, the idea is same. Okay. That you are going to put your filters at the top leftmost side and you will keep sliding it. Okay. That's the 3D convolution, but at just that most of the time we will be doing it 2D convolution in a 3D image. Okay. So what does it mean? That we only decide the width and height of our filter that you are going to use, and that generally the square filter. So you just decide the size, what size you are going to take. Okay. The remaining part, that is the depth. How much depth should I take? That generally depends upon the depth of the input. So if my input is a 3-dimensional, that is your RGB image. Okay. So as the example that I took initially, that my image was a 3 cross 224 cross 224. Okay. So I can take a filter of, let's say, size 5 cross 5. Okay. And the depth of this filter will be the same as the depth of my input, that is 3. Okay. So it's a 2D convolution in a 3D image. Okay. And it will look like this. Okay. The depth will be same as the depth of your input, and you will just slide it horizontally and vertically. Okay. And that's why it's called as a 2D convolution, because the output of this will be a 2D. Okay. Notice, unlike before, when we were doing it 1D convolution and the 2D convolution, when we did 1D convolution, we get an output in 1D. When we did a 2D convolution, we get an output in 2D. And again, as we are doing a 2D convolution, but on a 3D image. Okay. Still, we are getting a 2-dimensional output. Okay, or 2-dimensional tensor. Because the depth, we have kept it as the same as the depth of our input. If I have a 10-channel image or 10 depth image, I will take the depth of my filter that I am applying as a 10 depth filter. Okay. So the depth part will be like a constant, and you are just sliding your filter across the width and the height only. Okay. Just like it is done here.
What will be the size of the filter here?
The size of the filter, like if I take an example, if my input image is 3 cross 224 cross 224, okay, and I can take the filter like, let's say, 5 cross 5, okay, and the depth, because my input image depth is 3, it's a 3-channel image, so I will take the depth of 3 for my filter 2.
So it will be 3. Okay, 3
cross 5 cross.
Okay.
Yes, Chandra.
Sir, when we had 2D input and a 2D filter, the output was 2D.
Yes.
Right? Now we have 3D input and we have a 2D filter. Sir, then the output will be 3D or 2D?
2D. Because we have kept the depth of the filter to be the same as the depth of the input. Okay. And that's why we are just sliding our filter vertically and horizontally. And that's why the output that you are going to get, this is my output. Okay. It will be in 2D only.
So if the depth is not the same, then we will get a 3D.
Yeah, then in that case, that will be a 3D convolution that we will not be seeing in our course. Okay. So later, if you, I don't know if you watch the lecture, but tomorrow, when we are going to do the implementation, I will show it there. If you look at the PyTorch documentation, when you are going to type, just like we are going to do it for, in the case of ANN, we were doing it ANN.linear for the linear layer. Similarly, we have ANN.conv for the convolution layer. In that, it shows the variation, whether you want to do the 1D convolution, 2D convolution, and 3D convolution. We are always going to go with the 2D convolution, and we will set the depth as the same as depth of the input. Okay.
Okay, sir.
It's not like you cannot set it differently. You can set it, but that's a 3D convolution that we won't be touching upon. Okay. Yes, Shubham.
You said, like, you have told from like 3D, we are using the filter of 2D and getting the output as a 2D one. Like how I am not able to visualize that. How is the depth coming? Like what is actually the depth you are talking about?
So see, this cube that you have, it has a depth, height, and width, right?
Okay. Yes, because of it is 3D. Yeah, obviously.
Yeah. Okay. So I am going to take my 2D filter with the same depth as this cube that has. Okay, and because it has the same depth, it's like going to fit inside this box or inside this cube. Okay, and then I will just slide my filter vertically or horizontally. So it's like sliding horizontally. Now similarly, I can slide it vertically also. Okay, because we kept the depth to be the same, that's why we are able to do it. Okay, so the operation will be similar to what we were doing it now. Okay, if you like collapse it to depth 1, and it will be just sliding it vertically and the horizontally. Okay, same thing we are happening here also, because the depth
Sir,
10, it will just slide
sir,
vertically and then
sir,
horizontally.
in this feature volume, so if I actually consider the first 9 blocks,
Hmm.
so and the behind and behind, so they can actually tell something like RGB, the
Yeah.
and if the filter is like what we said, we can be a subset of the actual image height and weight, then what it means is that we are basically outputting for all 3 channels, but that is not we are considering in this course.
We are taking them together, right? Because we have kept the depth, we have taken into the account of depth, but that we have set it to the same as our input volume. Okay, so you are taking
Okay.
into the account of your RGB image or the number of channels that you have. Okay, but you are keeping it same as the input volume only, and that's why it's a 2D convolution on a 3D image.
So
Okay.
like as you told that the feature like you are getting the output as a 2D one. Like when we get the output, final output, like the depth will be automated or like something like the stuff will be
Yeah,
done.
that part we will come. Okay,
Okay, that's
it's
okay,
still
fine.
remain.
Yeah.
Yeah, we are still
Like
yet to discuss how we are deciding the final output here. What will be the size of that output? Okay. Now, as we have not considered the depth part here, it's still in 2D. So can we make it into more dimension like that? So that
so
part is
like
still.
we will go more into the higher dimension like 4D, 5D convolution like that stuff.
No, 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 no.
Okay, fine.
2D is
Okay.
what
Up to
we are going
3.
to study. Yeah. In 3D
Okay, fine.
also, we are not going to take into the consideration while doing the implementation and while doing the theory also. We'll stick to
Okay.
2D only.
Okay, fine, sir.
Okay. Yes, Karthike.
Like we did for 1D, 1D it was 1 into 1 plus 1 into 2, right?
Yeah.
So and then we add. So this is very clear. For 2D also you took 3 cross 3. So 9 elements will come and 9 elements we add. And then put it in one box, the output box. That is also clear. Here, how can you just show like A1, A2, A3, something like that? Small
That's
for
the main
every
part.
box.
Like it's a little bit hard to visualize how this will happen.
No,
Okay.
but you can say A1, A2, A3,
Yeah.
or
See,
A1,
for
B1,
now, part like
C1 is the filter, and then we know the input, and then we can just make
if you just
one.
stick to this part, there will be some elements here. Okay. Now,
No,
remember.
it is of what dimension? Filter is of
So,
what dimension?
so the filter consider this as a 3 cross 1 for now. Okay.
Okay. So A1,
But it will also have 3 in the depth also. So it's a 3 cross 3 cross 1.
Okay.
Okay. So there will be the depth also. Okay. Then the height and the width. Okay. And that's how you're going to fit this into just one piece of block here.
And this multiplication is going to be not matrix. It's going to be a simple star.
Yeah, it's going to be element wise multiplication. Wherever this filter is touching upon your input elements, those elements will get multiplied with those weights that are there.
So 3 cross 3 cross 1 means again 9 elements only will come.
Yeah.
So we add those 9
add
and then
those
put
elements and you will get one output. Okay.
And this 1 is R. The same way we have to do for 2, which will be G. And then the 3 will be like this.
No. 1 is not the R here because as I said, like the depth will be the same as the input depth. Okay. So the 3 cross 3 cross 1, the first 3 here denotes the depth of the filter. Okay. because your input is also, let's say, 3D, okay, then you have to take the depth to be 3. If your input is in 10 dimensional, or oh, sorry, not the 10 dimensional, 10 channels, okay, then you will going to take the depth of your filter to be also 10. So whatever your input depth is coming, you will take the same depth for your filter also. For the height and width of the filter, that you can decide, that's up to you. Okay, and because we have taken it for the visualization here, it's a 3 cross 1. Okay, so that's why it is. So 3 into 3 into 1.
Then we will get only 3 cross 1 in the output also, no?
No, you are still going to get one scalar value, because everything, every multiplication here will happen element wise. So all the elements that this filter is covering on my input, okay, will be getting multiplied, just like we see in the case of 1D convolution or the 2D convolution. They will get multiplied element wise. You will sum the output, you will still get a scalar value. Okay, and that scalar value you are going to store it in your output.
So it is a continuous process till we get the scalar value.
Yeah. Okay. And then that is for the one part, and then you are just going to slide this filter vertically and then horizontally. Okay. Yeah.
Maybe if we do one collab, then maybe we will understand.
On the collab, we will be doing it tomorrow. Okay. At max, we can do like one example later in the today class, numerically.
It's already later the day, so the mind is tired. So thank you.
Yeah. Yeah, maybe rewatch it tomorrow when you get fresh. So Priyanshu, what's your query?
So is there any site where we can visualize and play around with CNN?
You might find it. I'm not sure, but yeah, there might be certain sites which can help you visualize this operation.
So sir, can you please check and let us know in next class?
Yeah, sure. Yes, Dilip.
Okay, what I understood from your discussion, to make it simple, this the input layer, which is a 2D one, and we are placing it on the layer by layer. We got here is 3 layers, so each layer is coming in a row. I mean, my output is becoming a row in 3 cross 3 matrix. So each layer, in my input 3 cross 1 is putting in one vector, I mean here one layer, and the layer is 224 by 224 or whatever may be. I'm just placing on over it and becoming one scalar value, which becoming a cell of my matrix. And so one layer is becoming a row, second layer is coming to a row, and third layer is also coming to a row.
Yeah.
Yeah, that's right. Thank you.
I think it's 2D output versus 3D output. Okay, so it depends upon, you will see this later. So what you are going to do is, you are not just going to stick with one kernel, in which you basically go with like multiple kernels and get multiple such outputs. So the advantage whether you will be getting a 2D output or a 3D output, instead we just not only sticks to a 2-dimensional depth or like depth of 3, we actually go with more than 3 depth while doing the convolution operation. Okay. The main advantage we are going to see it, I think tomorrow it will be more good to visualize using Colab. Okay, but theoretically, if I tell what happens when you do the convolution operation on an image is each convolution operation or each different type of filter actually capture different type of relationship or outputs for from the image. Like one filter can be used to capture the edges that you have in your image. One can be used to capture the vertical edge, horizontal edge. It can brighten the image like that. Yes, Avira.
Sorry, sir, I joined late. I just want to ask, like, is it week 3 or week 2?
Week 3.
Week 3.
Yeah.
So I'm not able to understand anything. So I will check the recording. Recording you will give, right?
Yeah. Recording will
Okay.
be there.
I have to check the recording then. Okay. Thank you very much.
Yeah. So as I was telling, like from doing one convolution operation with one filter, you are going to get one output. Okay. Now we are going to call this output as feature map. Okay. So we got this 2D feature map. Now what we are going to do is we are going to use multiple different kernels. Okay. And each different kernel will going to give you a different output. But of course, we are going to do them in such a way that the output dimension is same. That is, as one kernel is giving me an output dimension of 3 cross 3, I will keep it consistent that others should also give me 3 cross 3. Okay, that part remain consistent, but the values inside my kernel filters will be different for each of my kernel. Okay, the advantage of using this is as this convolution operation that we are doing, it helps us capture different types of relationship or feature extraction from the images, like the edge detection. Okay, it can brighten the image, it can blur the image. Different type of features we can extract using this convolution operation. Okay, so that's why we use different kernels. Of course, number of the kernels that you are going to use is still like a hyperparameter. Okay, and then we will stack the output of all those filters that we have got. So let's suppose if you have used 10 filters, okay, then each of the filters will give you a 3 cross 3 output. So we'll stack those 3 cross 3 output. So the final output that you are going to get will be having a depth of 10. Okay, so it will be a 10 cross 3 cross 3. Is it clear? Yeah. So now, first terminology, that is padding. Okay, so previously, as you have seen here, that in this case, so we'll again stick back to the 2D convolution. Okay, so the input size is 1, 2, 3, 4, 5. Okay, while the output size is 3 cross 3. Okay, so the output size got reduced. Okay, in the case when you do not want to reduce the output size, okay, we generally apply what is called as the padding. Okay, padding is nothing but we will add the layer of zeros. So if you apply padding of 1, it's basically 1 0 row column like here for entire thing. Okay, so we'll apply this padding throughout the image. Okay, it helps us secure the original input size. Okay, another advantage of using padding is it also helps us gain the information from the border of the image. Okay, because generally when you are going to apply the kernels, it's like going to start from here. Okay, so the edges information or the border information is generally lost or it's not getting captured much. Okay, so that's why we apply the padding so that the edge information, okay, should also be get captured. Okay, so that's what padding is. Yes, Kailash.
Sir, we will apply this padding to the original image.
Yes, to the original image, or you can apply it intermediate step also. Like if you got any output from the convolution operation, on that output also you can apply the padding.
Okay.
So this is how you are going to apply the padding. Yes, Karthikeyan.
Original image makes sense, but after getting the output having a padding, what it helps? Because
Again,
output is already there, right?
Yeah, output is already, but similar to like your neural network case, you are not just going to have one hidden layer. You will be having multiple layers, right? So here also we will not be just doing one convolution layer. We will be having multiple convolution layer and followed by other layers also like pooling and fully connected that we are going to see later. Okay, and
after that maybe we can understand this because I'm still not able to get it. Okay, no.
And the reason is the same, that one of the major reason why you apply padding is you want to retain the same size that you had in the input image. Okay. Another is you want to capture the border information also. So for that also you apply it.
Yeah, that's clear. That those two things are clear, and then adding a padding over the original image makes sense because you go and slide the filter so that the edges will be captured because you have a zero above,
Yeah.
in the corners and then edges as well as the sides, so that we are capturing those edges as well as the corners. But
Yeah.
after getting the output, adding zeros and then making it as an original image, how really it is helpful, I'm not able to visualize.
Okay,
But
after
so
getting output, you will again see, because you want to now feed it into the another convolution layer. So after that also you want to retain the same
but
size.
something will be missed from the original already, right? Because you have the output. Because the next step already, if you are not adding in the original image, in the next step something is already lost.
Yeah, so if you want to
Then
add, you will
you
generally
later
start
give
adding
you.
it from the initial part only. So we'll add it in the initially, you can add it in the middle also.
Okay, maybe middle is for some cases. Maybe for that we need to go much more. Okay, no, okay, let's proceed.
Yeah. So next thing comes here the stride. Okay, stride is basically the part like how much rows or columns or basically the pixels you want to take in one go or you want to skip. So till now, whatever the convolution operation that we were doing it, they were called the convolution operation with stride of 1. Okay, that is because they were going over all the pixels that you have. Okay, so we started with here. Okay, then we quickly skipped it to here. Okay, and then again from here. Okay. Now, if you look at in the case of stride equal to 2 case, okay, we started from here. Okay, now technically we should now do this type. Okay, but we will skip this part here and we'll start from here. Okay, that's the stride of 2.
So we are giving a basically a gap, right?
Yeah,
One
gap.
extra gap.
And that gap will be in both case, vertically also and the horizontally also. As previously we were starting from here in the next part, right? But now we'll start from here. Okay. Okay, so that's the stride operation. Now, as padding is used to retain the size, stride is something that is used to reduce the size. Okay. And it's generally applied in the pooling layer that we'll see it later. Now, the formulas and the parameters. So we were discussing it how like what will be the output dimension, right? So that's generally come from this formula. Okay. So if you have an input width Wi, okay, and if you are applying padding to it, okay, because padding is getting applied both in the row wise and in the column wise also, or width or height wise. So it will have like add 2 more width and 2 more height. Okay, that's why the new width after applying padding will be Wi plus 2p. Okay, you will minus the filter size from that. Okay, and then you will take the floor function here. It's not the dividend. Okay, it's the floor function. It will be there if it's not divisible, divided by s, because that many pixels you are skipping, and you will add 1 to it. Okay, that will be the output for your convolution operation. Okay, so using this formula, you can determine that if I have the input width is Wi and I am applying padding of p, I have a filter size f, I'm using the stride s, then what will be my output width? The same formula apply for the height. And depth, as I said, depends upon how many filters you are using. Because one feature, one filter will give me a will give me an output map of WO cross HO. If I am applying 10 such filters, okay, then it will be like 10 cross WO cross HO. So the depth of the output depends upon how many filters you are using. Is it clear?
Here the filters, you mean the number of convolutional layers, right?
Not the number of convolution layer. In one convolution itself, you can apply multiple filters.
Oh, okay.
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 So the number of filters that you are applying is K. The filter size is F. Pad is S. P is padding. Okay. So the output depth is the number of filters that you are using.
So the actual depth?
That's the input depth. That is DI.
This D naught won't get affected because of the actual depth.
No. Okay, depends upon how many filters you are applying directly. Yes, Dilip.
Why are we using many number of filters in the same image?
As I said, different filter can help you to gain different type of feature extraction. One can detect edges, one can detect like it can blur the image, okay, so it can brighten the image. So each filter operation or the convolution operation can help you get different kind of result. So that first take multiple such results. Okay. Yes, Shubham.
So like the basically in the DO is equals to K. K is basically the W part, right? W, the length
K is
of W.
the number of filters.
Yeah, in the example what you have shown using W, that one you are telling about the number of filters you are telling.
So the number of filters, like as I said here, now here I am using one filter. Okay, this is my filter that I am using and using which I got one output. Now I can use a different kind of filters. I mean with the same dimension of 3x3 and apply it. And using that I will get another 3x3 output. Okay. So in this manner I can apply multiple kernel output together and stack them. So that's why I will have output dimension of the number of filters that I am using times the output width or output height.
So basically K is the number of filters, right?
Yeah.
Okay.
Yes, Mona Lisa.
Yeah, I'm actually going a few slides back. You can explain from here itself. When you say that we slide the filter over the actual image, the input, what is the intention of the filter? To cover the entire image, or it will just capture a few parts? Like, is it always necessary that the filter will always slide into all the different frames it is going to shift across the image?
Yes,
will
yes,
it cover all corners?
It is going to slide through all the corners. It's going to slide through all the entire image. That part is necessary.
Okay. Okay. Thank you.
Yes, Karthik.
I'm not able to understand this filter. When you say something, some filter to blur, some filter to sharpen, how this will be able to this kind of information? Yeah, I'm sharpening, I'm blur. How the blur image input? If I blur my input, my sharpen my input, how it will be is how this kind of information help to identify in the final. Because we need to classify, right? Classification means
See,
I need to
first of
understand
all, like these filters, okay, they are learned using the back propagation. So you do not put the filters in such a way that you already know what kind of output you are going to get. Okay, so you are going to just the way you are going to randomly initialize in your ANN, you are going to initialize your filters with some random values. Okay, and these filters are learned through the back propagation method. So they will learn the required feature maps for the final output.
So even there is a blur image, it will try to recognize. That is the
So
purpose
accordingly,
of putting these kind of filters.
the parameters in the filters will get adjusted based on how you want the output, and using back propagation, okay, these filters values are learned. So you do not like put
Is
that
is
I
it
want.
something similar to this? Like some apps are there, Snapchat and things like that. People put filter. Is it the same
Yeah,
kind?
same kind of things are getting used there also. If you like see in your phone, And that you can edit any
Yeah,
photo.
people
Okay, it
would
has the
put
option of to
filter after
sharpen the image, to blur the
Yeah.
image. Okay, so
Yeah. While taking picture also we do that
yeah.
sometimes.
Okay, so in that part also these things are working. They are applying one filter which is going to sharpen the image.
So below you've written there weights, the biases, what are that? Weights,
Yeah,
biases,
that's the
parameters.
number of parameters that I'm coming now. Okay, I just want to make sure, is it clear so far?
Sir, are these standard formulas written here, width, height, and depth?
Yeah, these are standard.
Okay.
Yes, Mona Lisa.
So these formulas are applicable for all types of convolutions, like 1D convolution, 2D, and 3D. It's
Yeah.
applicable. Okay.
Okay. Now comes the part of yes. Any more doubts?
Yes, sir. Why we are adding one?
Okay, that you should try to figure it out. Take one small example. Okay, and in that you try to figure it out what will happen. Like try to manually just slide the filters. Okay, and try to predict what will be the output case. Okay, then you will be able to understand why we are adding the one here. It's not intuitive in the first case, so you will be only able to get the hang when you are going to just try it with a simple example.
It will work for the 2D convolution example you gave us.
Yeah, so in that, yeah, like, you can put the values and you will get the answer. Not a problem. Yeah, so main part is then.
I have a doubt.
Yes.
See, the professor explained about the receptive field and kernel size. And also in the padding, he has talked about two different types of padding, zeros and same.
Yeah. So
If we
the
can
zero
touch
padding
upon
is
them.
yeah. So there are two types. One is the SAM padding, and one is the valid padding. Okay. So SAM padding is like you want to retain the same. You will apply the padding until you get the same output size as your input size. Okay. So if your input is 224 cross 224, you want your output of the convolution also to be 224 cross 224. So that's the SAM padding. Valid is you do not apply any kind of padding. Okay, or padding is equal to 0. In the PyTorch, you have this option of padding parameter in which it accepts a integer also. Like you can define whether you want to add the padding of 1, 2, or 3. Padding of 1 means you will add the 0 in the row wise, column wise, both. Padding of 2 means you will add 2 rows of 0, 2 rows of 2 columns of zeros. Okay, same thing. Or you can use the keyword also, like SAM padding or valid padding. Okay.
Okay, got it.
Yeah. So now comes the parameters. How many parameters you will be having? So as you have a filter of size f cross f. Okay. So you will be having f square parameter from here. And the depth of the filter, as I said, it depends upon the depth of your input. Okay. So f into di. That's the total number of parameter in one filter. As you are going to use k such filter, there will be f into di into k total weights. Okay. Now bias will be k because there is only one bias that you add in one output image. So let's take this example only. So we applied our filter on this image. We get this output. Okay. Now you are only going to add one scalar value to each of this output, or that will be your bias for this one filter. Okay. So one bias for one filter, and as you have k filters, so total k bias will be there. If you are just going to add these two, okay. So if you just add these two, you can take the k common and the total number of parameter in one convolution layer. Okay, would be f square times di plus 1, the whole thing times k. Okay. Is the calculation clear for the number of parameters? Okay.
So it's just
Here
key
the
times
weight,
weights.
One by one.
yeah, here the weight you are saying that the filter will have some numbers over it.
Yeah.
That is called weight. Huh? Okay.
Yes, correct.
And after multiplying whatever we are getting, we will add one bias to that. That is the okay.
One bias per filter.
Perfect. That will be added to all the values.
Yeah.
Okay.
Yes, Shubham.
So like including the stride, it will make a great change to the output layer, because it will change the whole dimension only. The stride part.
Yes, stride part is going to change the dimension, but our number of parameters does not depend upon the output size or the stride or the padding. It only depends upon your filter size and how many filters you are using and the depth of your input.
So like you go back to the previous slide, like where you showing the AC equal, yeah. So in this case, how you will get the output matrix?
The output matrix will be this 2x2.
Yeah, but the input one is very big and we are getting a small part of this.
Yeah.
So will it will affect a lot, I think. It will capture a small part of the image, I think.
Yeah, so see, at some point of time you will try to reduce the size also of your image. Okay. So but what you will do is at that time you have already captured the information, because you have applied so many filters and stacked them together. So you have already captured enough information. So now you can work around with the smaller size or reduce the size also.
Yeah, understood. Okay, so fine.
Okay. Yeah. Yes, Karthikeyan.
This parameter, what is the correspondence of this parameter in this convolution neural network?
So these are the
to
parameters.
The normal one, normal we did, right? ANN.
Yeah.
What is the corresponding thing here?
So there also we learned the weights and bias, right?
So weights we understand, bias we understand. Now we introduce a new term called parameter. We did not say there. We did not call it as a parameter, right? We call it weight and bias. Why we are introducing this term called parameter here?
So
can it weight and bias itself suffice, right?
See, when you call it like parameters, it includes both weight and bias.
Yes.
Okay. So if in questions it ask you to find the total number of parameters, it means it is asking you to find the total number of weights plus the total number of bias until it explicitly
there we were
says.
not introduced. Now we are introducing this term for this.
I think it was introduced there also.
It is in MLP itself.
Okay.
So in MLP we had right number of parameters.
Estimating the number of parameters.
Okay.
Yes, Anshuman.
Yeah, so I just needed a clarification. Let's say I'm going to apply K filters. Let's say, for example, K is equal to 3. So all three filters would be applied on the input image, or the second filter would be applied on the output of the first filter?
No. All three will be applied onto the same input image.
And then we'll create a stack.
We will stack the output of those, and that will be like kind of your new input, and that will be fed into the next convolution layer.
Okay, all right.
This will proceed. Shall we move ahead?
Yeah.
Now, in more detail, if you see, you have an input, width and height are 3, depth is 1. Okay. You have the filter, weights are W11, W12, W21, W22. Okay. So my filter size is 2x2. We will be using the stride of 1. That is, we are not going to skip any row or column. We are applying padding of 0. That is, no padding is applied. Okay. K is 1. That is, we are only using one filter here. Okay. So that's the convolution output that you are going to get. If you put these values in the previous slide formula. Okay, that was Wi minus f plus 2p. So that is 3 minus 2 plus 0, so 1 divided by s, so 1 by 1, 1. And we add plus 1 extra, so 2. So that's why the output will be 2 width. Same for the height. So 2 cross 2 output you will get. And because we are only using one filter, so the output depth will also be 1. Okay. Now, the first part of the output is this W111 into X11 plus W12 into X12, W21 into X21 plus W22 into X22. Okay, as you are going to apply your filter on this block. Okay. The same will work for the remaining part also. Okay, as you are going to slide it. So W12 into X12 plus W12 into X13, W21 into X22, W22 into X23. Okay. Now you are going to also add bias if you want to add. Then you will add one bias in all of these 4 output that you got, basically for these scalar values. Okay. Now, convolution is also a linear operation. So each convolution operation is followed by non-linearity. Okay. That is whatever the output you got. Okay. You will apply ReLU or any other activation function element wise on each of that output to get a non-linear output. Okay. So till now, I hope it is clear.
Yes, sir.
Okay.
This is also
standard
net. The dollar always the last line of the last character. Now this is how you would move up and down.
Yes, Pranshu.
Sir, in previous slide, whatever we got that output, now we are just passing it through some ReLU activation, right?
Yeah, yeah. Because convolution is a linear operation. So you want to apply the non-linearity also. Okay. Yes, Shubham.
So basically, the first part is like bit similar type of what we do in the agent, the linear part, and then transform to the basically the same thing we are doing with the images also. Like here, the image will come only.
Yes.
Okay.
Now we have seen the convolution part. There are 2 more things that are remaining, but they are not that hard. If you have understood the convolution, then you will be easily able to understand the max pooling and the fully connected layer. Okay. So basically, there are 3 different types of layer in the CNN structure. Convolution layer that basically does the convolution operation, max pooling that we will see, and then the fully connected also. So max pooling is similar to like what we were doing it in the convolution, but here we apply a special type of filter case. Okay. So what does it mean? I have this image. Okay. I have some elements in this. Okay. Now here also I'm going to apply it 2 cross 2 filter. Okay. Now what I'm going to do it now here, that this term max pooling, it basically refers to that if I'm applying filter on this part or this region of the image, I'm just going to extract the maximum value in this region. Okay. So the maximum value in this region is 5. Okay. Then I will again slide my filter. It will now apply it here. Max value is 6. I will now apply my filter here. Max value is 8. Now I will apply my filter here. Max value is 9. Okay. So this is the
max value depends upon the filter value also, no?
Not the filter value. In the max pooling, you are just doing the max operation on the output of convolution operation that you got. So this is like
so what will be the weights in the filter matrix?
No.
Okay.
Max pooling does not introduce any more parameters. Okay. The reason why we use max pooling is generally to reduce the output size. Okay, and that's the reason why we start max pooling with stride of 2 and filter of 2. That's the like general or like a default case that we generally use for the pooling layers. We use the filter of size 2 cross 2 with stride 2 with padding to be 0. Yes, Pranshu.
So, sir, is this still part of CNN?
Yes, it is also part of CNN. As I said here, in the CNN, you have these 3 layers. Convolution layer, in which you are going to do the convolution part. The pooling layer that we are seeing it now.
Okay, sir. And sir, when we do this max pooling, does it retain the features or would it lose some features?
Of course, it's going to lose some information. Okay, but we are okay with that because when we apply the pooling layer, okay, we have already accumulated some amount of good information using the convolution operation. So now we try to basically want to reduce the size. Okay, so that's why a general setup for the pooling is we use the stride of 2, filter of size 2 with padding to be 0. Yes, Shubham.
So when we use this pooling after done with the convolution layer, right?
When I will come to this part a little later, when I will explain the remaining layer also, and then after that I will again come back to this structure. Okay, then I think it will be more clear.
Yeah, so like you are doing this part, like you are just giving an example. You have not told that where we are using this, right?
Yeah.
Okay, fine.
I'm just explaining what is pooling layer. So this was part of max pooling. Yes, Karthika.
What is the purpose of reducing the size in this pooling?
Yeah, that's
the size,
because at some point of time after reducing it, you will feed the output to the fully connected layer. That is, after reducing it the size, you are going to flatten the output, and then the rest part will be followed as the ANN structure way. That's why we want to reduce the size, because initially we cannot do the flattening part, because in that case it would blow up our parameters. But if we extract the information in such a way that we gather the information using convolution operation, and then after applying the pooling operation, we reduce the size, and after that we will going to flatten it. Okay, that's what happened in the flattening.
Without this pooling, we can choose the filter and then make the size itself is smaller, right?
Yes,
because
yes.
based on that, your output you are reducing, right? 4
Yeah,
cross 5,
that you can do, but
4 cross 3 or 2 cross 2 also you can make based on your filter.
Yes.
When we should do this pooling?
Yeah, but one point that I mentioned here, that pooling layer does not introduce parameter. Let me write it down.
Yes. Because taking max we are losing. Why we need to lose something? Or there is a trade-off. Your filter and pooling, there is a trade-off.
Yes, there's a trade-off because we have already applied the convolution layers and the filters layers, so we have already extracted a good amount of information. So now you want to reduce the size.
Anyway, it's both are hyperparameter used, right? Even filter is hyperparameter. Here also hyperparameter, so it will find a trade-off to get the optimum number as to flatten.
Yeah. Okay. So why see, one thing that you noticed good, it is that like we could have done the same thing in the convolution layer itself, but in the convolution layer it will introduce more parameters. Okay. The pooling layer, the main purpose of them is to reduce the size. Okay. And the general trend is we use a stride of 2 and filter size of 2. Okay. If I take an example of, let's say, 6 cross 6 input image with the stride 2 and the filter of 2 with padding to be 0. Okay, using the formula W minus F plus 2P by S plus 1. Okay, it will be 6 minus my filter is 2 cross 2. Padding is 0, so it will be just 0. Stride is 2 plus 1. So it's 3 by 2 plus 1. Okay, now as I said, we use the floor function here. Okay, so it will be 1 plus 1. 2. Okay, so it's almost like to do the half of it. Oh, sorry, here it should be 4. So then 2 plus 1, 3. Okay, so when we apply the pooling layer, it basically does the half of your width and height. Okay,
why do we do this? Because this filter itself is hyperparameter. Based on that, this output is anyway going to come. Why we calculate how much is the size? Why we care?
See, if you do not care about, then you cannot initialize next layer, because you should know what's the output here. Only then that output can be fed into the next layer. And for that, you should know what's your input that's going to be, right? Because this output will be
That
fed
is
into
only
the
starting, right? Since it's a hyperparameter, means it is going to decide on its own what is the best filter.
hyperparameters. You decide on, not on your own. You have to decide your hyperparameters.
So that
Parameters
is
are
beginning. Beginning, I will set something to start with. Okay.
sorry.
I'll set something small. To start with, I will set something small. If I have a 10 cross 10, I will start with 3 cross 3. And then
Yeah.
anyway, it's a hyperparameter. It will get tuned. And then why do we find all this? I don't
See,
understand. Why
you
should we find
apply
every
a convolution layer, you will get an output. Now you are not just going to stop there, right? You are going to then use that output and feed it into the next layer. And because they want to create a new layer, you should know what's that input going to be for that. And what's their size. Only then you will be able to create it. Okay, so let me take the example of the NN. Okay, suppose this is your input layer. You have this one hidden layer. Okay, and this is a fully connected layer. Okay, so you'll here have weight matrix of size 3 cross 2. Okay, now you want to feed the output of this operation here to the next layer. For that, you should know what's the output of in what dimension this output going to lie, right? Only then you can create the next layer based on that.
Okay.
Okay. Like, and if I take it in the form of convolution layer, you have your input. Okay, you will apply your kernel. You will get output in some other dimension. Now that output will be fed into the next convolution layer or the pooling layer. It can be. Okay, but for that, of course, you have to decide what should be your this output is, because you will decide your filter in how. The filter is decided based on the depth of the filter specifically is decided based on the depth of the input that you are going to use, right? Correct. So for that, you should know the dimension of this. Okay.
Okay.
Yeah. So I hope it was clear so far. So this was the
The
max
question
pooling.
was like, so the question that sir has asked, like, why do we need to take that value, right? The question I want to ask.
Which value?
Like, sir, what question sir has asked? That's I'm asking.
So he has asked like, why should we care about this output? Why we are calculating it? So we have to calculate it because that output will be now fed into the next layer. Okay? And for that, you should know what is the dimension of this output. Only then you will be able to create the next layer. Okay.
Yes, yes, sir.
Yeah. So what is shown here is the max pooling operation. Now there are other type of pooling also, like the average pooling. So as here we were doing it the max operation. Instead of max, now you can do the average operation also. So that will be the average pooling. Okay. We have max pooling, we have average pooling. Okay. These are the two now. The final thing that is remaining is the fully connected layer or FC layer. Okay. So what happened in the FC layer is, after doing some convolution layer in the pooling layer, you have reduced the size to some manageable extent. Okay. Now the size is in such a way that you can manage it. Okay. Unlike the initial size, in which case the number of parameter will blow up. Okay. You have now reduced the size. So after that, you are just going to flatten the image, and then the latest structure will be the same as the structure of your ANN. that this flattened image will be connected to a hidden layer, and then that hidden layer will be connected to some another hidden layer you can add, or the final classification add you can take. Okay, so that's your fully connected layer that you are going
So
to
here
flatten.
also there will be weights.
Yes,
in
yes.
this
Here the weights,
connection.
yeah. Here the parameters will be there. Okay. Only the pooling layer does not introduce parameters. The fully connected and the convolution layer both introduce new parameters. Okay.
What about activation functions? Are there anything?
Yeah, see, activation functions will all be not in the pooling one, but after applying the convolution, you will have the activation function as we discussed. And similarly, as we are following the structure of ANN here after flattening it, so as we apply the activation in the ANN, here also we will be applying the activation after doing the linear operation. Okay. Now I will come back to this architecture that I initially brought it up. So suppose this is your input image. It's more than 3-dimensional or 3-channel image. Okay. You are going to apply filters on this. So you can apply more than one filter. Okay. And the number of filters you are going to apply, that will decide the depth of your output after doing the convolution layer. Okay. So the operation that you are applying on this image is the convolution operation, using which you will be getting a feature map. Okay. And you will stack all your feature maps together. So that's why, like, this is your first feature map, as you can see. Okay. And you are going to stack each of these filter maps that you are going to get from different kind of kernels. Okay. So now this will be your new input that will be fed into the next layer. Okay. So the next layer can be pooling or the convolution. Okay. So unlike the case of your like ANN, where the structure was kind of fixed, you have input layer, then some hidden layer will come, and the final output layer. 2 minutes, Karthik, I will come back. Okay. Here the structure is not so fixed. Okay. You will have an input. Okay. Then it can follow with the convolution. It can have the max pool. Then it can again come with convolution layer. Then again I can apply the convolution. Again I can apply the convolution. Then I can apply max pool. I can apply max pooling or average pooling. Okay. So it's not fixed like you apply first convolution layer, then max pooling layer, then convolution. It can be like you can apply 2 convolution together. Okay. Then you apply max pooling continuously. Okay. So that structure is not fixed here. Okay. And then after that, at certain point of time, when you're satisfied with your like current size, that now I shrink it to the manageable extent, you will apply the flattening followed by a hidden layer, then the final output layer. Yeah. Now Karthike.
This diagram represents from the input I add the filter, right?
Yes.
This filter depends on the filter, because the third column, it is increased. How it has increased?
It's not increase, it's shrink only.
Shrink only.
Okay, it's just looking maybe from
okay,
the
increase in the sense that consider the channel, because
you mean depth. Yeah, depth you can increase,
input
right?
Input is 4 channel, assume.
Okay.
And I apply how many filter? 1, 2, 3, 4 filters. Right?
Okay. Then this will also have a 4 depth if you are applying 4 filters.
4 filters, 4 depth.
Now here you can apply 10 filters, then you will get 10 depth.
No, where is the output? Where is the output?
See,
first
this image is
there, right?
see, this is the image.
Yes.
Okay. On this image, you are applying this filter. Okay. Please turn it off. Okay. After applying the filter, you will get this feature map. So this is the output. Okay. What's showing here is the output. Okay. And now on this output, let's suppose these are all the convolution layer. There's no pooling layer. Let's suppose that. Okay. Then on this output, I am going to again apply my filters. Okay. That filter I am applying. Okay. So then again I will get this output. Now the number of depth is increased because I have used more filters here now. Okay, let's suppose here I used 4 filters, so the depth of this output will be 4. Then on this output, let's say if I use 10 filter, then the depth of that output will be 10. Okay. Yeah.
So
Now Shubham.
basically depends upon the weight only, right? It's basically depends upon that weight vector only. That what will be my output.
Yeah, yeah. It depends upon your filter size. Okay.
Yeah.
And the
So
stride
like,
and the pooling also.
yeah.
Oh, sorry, stride and the
Yeah.
padding also.
Padding, yeah. So like say, can we imagine like this? Like we give a basically input layer and all the others like in ANN we have the neurons and here we have the 3 layers like convolutions and the FC and the pooling layer. So we can do anything over there.
See, the pooling layer is applied at, oh, sorry, not the pooling. The fully
FC.
connected layer is, FC layer is applied at the end. Okay. The pooling and the convolution. Okay, they can
So
be
we can
used
do
anywhere.
anything. Yeah.
Like we start with the convolution, of course. Okay.
Yeah.
But it's not in this fashion like every convolution layer has to be followed with a max pooling. It can be like you apply convolution layer, then again you can apply the convolution. Then you can like apply max pooling and again max pooling, like that also can work.
So 2 layers are fixed, like not 2 layers. Input 1 is fixed and the FC layer is fixed. Between that we can do anything.
Yeah. Between that we generally start with the, you have to start with the convolution.
Yeah. Obviously,
after that, there's no fixed pattern. Okay.
So what the last layer looks like it has been doing here. What's that? Yeah.
This one is for the classification. So let's suppose if we are training the fashion MNIST, okay, then this layer will have 10 neurons, okay, in which you will apply the softmax to get the probability for class, whichever class has the most probability.
Okay, sir.
Okay.
So this will again it will go for the back propagation and update all the weights.
Yeah,
even
update
the convolution weights also will get updated.
Yeah. Yes.
Okay.
Okay. I'm not sure whether we will be seeing the mathematical expression of back propagation in our course for the CNN. As it is not there in the week 3, let's hope it's not there in the week 4 also. Otherwise,
So like we will be given the questions based on the back propagation on this network.
Yeah, that's what I was saying, that in the week 3 the back propagation was not there, at least
No,
from
it's
mathematical
not
point
there.
of view.
It's not there in week 4 slides also.
Okay, so then, okay, you are lucky. Then we will not be studying it from mathematical point of view. Okay, but yeah.
So it would be very complex in mathematical form.
Not so complex if you break it down into simpler parts, like how the convolution is happening. Will look a little bit complex in the starting, but you will get the hang of it. Yes, go on.
Sir, are the total number of parameters in a CNN are less than the, let's say, if we were using like a traditional ANN?
It depends upon, again, same thing, like how many hidden layers and the number of neurons that you are using in the that network structure, right?
Let's say we are using like a CNN and we apply a lot of filters and the amount of parameters are almost the same. Then basically, then it's like we don't have an advantage.
You don't have an advantage in terms of parameters, but remember, I also tell one thing, that the destruction of the spatial features, okay, it will lose the position of the object that you have when you flatten it in the classical ANN case. Okay, that case is preserved in the case of CNN.
So, like effectively, let's say we are using a sufficient amount of filters. In that case, the spatial, basically preserving the spatial, like that is the only advantage.
Yeah, those advantages are there. Okay. Yeah. So there are a few more things that we will be studying now. Is some advantage of or key points about the kernel, stride, pooling, etc. Okay. So first of all, is the structure clear for the CNN? How the things are flowing in the forward propagation?
Yes, sir. Yes, sir.
Yeah, so some key points about the kernels. One, I have already mentioned that they are learned. Okay. So just like your ANN case, you will initialize them randomly and then you are going to learn them using backpropagation. Okay. Now, second is
You don't always need to create a file first and then start working on it.
it does increase
Create a
the receptive field. Okay, so what does this mean? Yeah.
Or you can also do it.
So you have this image. Okay. Now you are applying a filter on this. Let's suppose you are applying a 2D filter. Okay. Now this filter in the first part has only look at these 4 position in your input image. Okay. So after doing this, you will get some output. Okay, the output dimension might be incorrect. Okay, I'm not calculating the output dimension here. Okay, so when you place one filter here, you will get one output. Then you are going to slide it. You will get another output here. Okay, and similarly, you are going to get it here also, and then here. Okay. Now, what I'm going to do is we are again going to feed this output to the next convolution layer. Okay. So for that, what we do, we again apply the filter on this. Okay. So let's suppose if I again use a 2x2 filter. Okay. Then this is my current red filter that I'm using. Okay. That filter is currently looking at these 4 positions in my output of my first convolution. But if you go back a little bit, these 4 positions come from where? The first position was the result of convolution operation between these positions. The second was the result from these position. Okay. This was the result from this position, and this one was from this position. Okay. So applying this filter in the next convolution layer. Okay. It's actually helping me to cover this big part of the image. Okay. So that's what it means by that when you stack this multiple filter across the different convolution layers. So I should add this one more part. Okay. It's increase your receptive field or now this filter because going to look at this big part of the image. Okay. Now, one thing that one can ask is why can't we use the big filter in the starting point if you just want to look at a bigger picture of the image? It's just there's a trade-off between the size of the kernels that you are using or the size of the filter. Small kernel filter size will learn the local feature. Okay, because just you are going to look at a small neighborhood. Sometimes it's useful, sometimes it's not. Okay, while the larger one will look at, of course, the global one. Again, sometimes it's useful, sometimes not. Okay, so what a general trend we do is we just apply a large filter only in the starting layer. Okay, once you go into like after 2-3 convolution, you do not apply a big filter. And the maximum the general trend to apply the filter is like at max 5x5 or 7x7. Okay, I think in the week 4 we are going to look at different architecture of the CNN, like the VGNet, RSNet, etc. Okay, there you will be seeing that you do not apply a larger convolution generally. Okay. Yeah. So is the second point clear?
Yes, sir.
Okay. So more left with this. So one more point here is stacking remains a linear transformation. See, stacking by here means like okay. So for the staking by here, I mean like once you do the first convolution operation, after that you will get the output. Okay, and then when this output again is going to feed into the next convolution layer. Okay, that is kind of like here, if you understand, on this image, here is my filter. I got this output. Now on this output, here is my filter. I got this output. Okay, so now on this output, if I am going to apply this filter, okay, for this output, this filter is looking at just this small portion. But if you just look at through it with the channel of like input image, it's going to look at a very big picture of it. Okay.
I want to move to line number 4. I press enter. I am at this character. Now when I will press dollar, just it immediately went on the last text of the.
So one more thing is here, that is sometimes you use the size of 1 also for the filter. Okay, that's not going to reduce your size for your input image, because if I just going to use a filter of size 1x1, then I'm just going to get the same output. Output dimension will be the same. Okay, but that is useful in when you want to apply the non-linearity and you do not want to lose the dimension. Okay,
so that filtering has no effect, but if you want 1x1 only, then the whole image is that only. No? What is the use of that?
No, it will have effect because you are applying it, you are multiplying those input values with the weights, right? So it's a convolution operation.
Yes, weights we are multiplying.
And then you are adding the non-linearity also on the top of that. Okay, so it will help us learn the non-linear feature, okay, without losing much information. Can it cause overfitting? Yeah, it can cause overfitting. Okay, as in, of course, if you increase the complexity, it can cause overfitting. Okay, so that's clear. Move on to about Shubham.
Yes, so like in other models, we have seen that we are giving something data and it's being learned and it's produces the predictions or the outputs. So here, if we give any image, like how can we make it generate an image, like our own custom images?
CNN can be used to generate an image, but so far in the week 3 we have not seen it, how it do it. Okay, but you can use it to generate an image also. Okay,
like we need to do some like changes in the net architecture.
Not in the architecture, we are not going to change it. It's just how you do the backpropagation and all. Okay, you tune the network in such a way that it's generate a special type of image.
So it will depend in the FC layer, right?
Not in the FC layer. See, basically you are going to backpropagate with respect to your input also. Okay, so what you can do is in the input, you can feed a random image, a random pixel image, and then you will the forward pass. Okay, you will have one class. Okay, then in the backward pass, you are going to change the input also. So that's what you can do to generate an image. Okay, so but that part till now it's not covered in the week 3, so I will not go into in much detail. Okay, but other methods are also there to generate an image that I think you will be seeing in the generative AI part. Okay, the GAN is there, autoencoders. Okay,
the visual mode we use in very restricted, in very limited cases. Third one is.
So now some points about the stride and the pooling. Sorry, stride and the padding.
Okay, so 1 and 3 are.
So first, as I said, the stride.
What is escape mode? Escape mode is where we will type commands. Okay, it is not called commands actually, but we will just type some keys to make the changes. Okay, I told you.
So stride is used to downsample the image size or reduce the image size.
Double D.
Okay.
Okay.
The padding. Okay.
Double D.
So
deletes the.
We have the same padding.
Okay. Now this double D
Okay,
will work
so
only
you'll
in the
get
escape.
enough padding
If you are inside the insert mode, if you are inside the insert mode,
to get
you cannot do double D and expect it to be deleted.
output
Okay, so there are
size
three different modes. First is the escape
same
mode,
as input
second is
size.
visual mode, and third is insert. Okay, so the
Okay,
most important
and
ones are
another we have the
escape mode
valid
and
padding.
insert mode. Visual mode is not used
Okay,
a lot.
that's simply like no padding is
Also,
applied.
it makes certain things easy, but it is not used that often. Okay, so what is escape mode? Escape mode is where we will
Okay,
be typing all the commands.
and why we apply padding?
Escape
It's
mode,
basically
escape mode only. This is by
to
default.
improve.
The default mode is escape mode only. Okay. And here you can change, you can one line
At border or the edges.
other. Okay, this is how we can move from one line to the other.
Okay,
And how to enter escape mode.
so these things we have already discussed. The same padding, that is, you will add enough layers of zeros, row wise and column wise both, so that you will get the same output size. Valid padding, you will not apply any padding, that is p equal to 0. Okay,
How will you do it? You will do it by pressing the escape.
now about the pooling layer.
Okay. Any
Okay,
doubt till here?
so pooling layer is used to reduce the size. Okay,
Here.
okay,
Now to the insert mode.
with no additional parameter.
Mode is where here we will
Okay,
edit the
now this one thing that it does is
here we will
called as the
edit the file
translation invariant.
using the keys, using the keyboard. Okay, using the keys
Okay,
A, B, C,
so
D.
Prof have used this word, translation invariance. Now what does it do is it's basically about the position only.
Okay, and
So suppose you have this image. Okay, it's not taken here. Go back to our example for the image. Now, okay, so suppose you have this image. Now in this image, suppose your task is to do the classification. You want to check what is the type of fruit you have. Okay, so apple, banana, like that. So in this image, your apple is at this position. Okay, so when you are going to apply the max pooling, okay, the max value can lie here. Okay, now even if you like change the position of the apple somewhere else, okay, in that case also when you are going to do the max pooling, you will be able to extract the maximum feature from that, because still the maximum value will not change with respect to the pixels that it has in the images. So it does not matter at what position you have your object. Okay, the pixel values will be accordingly in that place, and we will be able to extract the maximum information or the maximum pixel value from that place. Okay, so that's what the translation invariance means. Okay, that even if like an object moves little bit in your different images, like in one image you have apple here, in another image you can have apple here. Okay, the maximum values still lie in that region only. Okay, wherever that your object is, because the pixel values will be accordingly in that region. So when you are doing the pooling, specifically like max pooling, okay, the max value that you will be getting will be the same. Okay.
Now A.
Yes, Dilip.
Insert. Okay, actually it is like
Here, are you indicating that while max pooling, there is every possibility that the image will image may change its position in the frame?
See, I'm not saying that like image will change the position. It's say like, see, you will be feeding different kind of images to the network, right? So in one image you can have apple here. In another image, it's not necessary that apple will be here only, right? It can be here.
Yeah.
Okay. Yeah. So that different position of image still can be captured. Okay. That's what I was telling.
Okay, and after you have entered into the escape mode,
Now that's what happened with the max pooling and the average pooling. It's basically to the smoothing operation.
Exactly, not bad.
Okay,
But exactly
so it's
not
like a
This is
smoothing
how
operation.
we use
All of the pixel values that are there in that
Okay.
region,
So
okay,
is this
as it
clear?
will do
We
the
will take
average of that.
screenshot of this
Okay, so
screenshot.
you'll get a
And now I'm
smoothing
gonna
or
start
smooth image representation
start going to the
for the output.
insert mode and start typing.
Yes, Shubham.
So the average pooling basically refers to the blurring effects, right? It will create the blurring effects, I think.
Yeah, it kind of creates the blurring effect.
Yeah, below the given line. Yeah, below the line.
As it will do the average of all the
The line
pixels.
we are in.
Okay.
If you press small O,
Like for example, sir, say put the so in that apple part, if we like paste the or give the filter over there, so in that red area, if we do the average part, what will happen? It will become red only, right?
Yeah, it will become red, but it will like blur it little bit because the pixel value will get averaged.
when you will
Okay, so it will not be like as clear as this. So it will smooth it.
those
It will do the average of it.
So sir, all the technologies like when we edit any photos or take the portrait modes, so this technology is only used of blurring things.
Okay.
Yeah.
Now,
Okay.
these are very important.
So there also we are applying the filters. Okay, of course, it's not, might not be the as simple as it sounds, but yeah, the basic idea is the same. Okay. So you can say like the building block for that is this one. So let me recall any more points.
Okay, but it is not as simple. Okay. First, you
Yeah.
have to yank. Yank is like
Next pull.
copy.
Uh,
First, you have to copy the context. First, you have to copy the lines.
Capture.
Okay. And then you have to yank it.
Most
Yank
prominent.
basically means paste it. The copy paste is possible in VI.
Okay.
Also,
average pulling.
This is these
to
are the ways
smooth
you can copy paste using the
feature representation.
features of the VI editor, but you can also use Control plus C and Control plus V.
Yeah.
Okay, these also
So,
work here. Okay, and remember one thing.
Okay, so that's mostly ends our discussion with the CNN part. Still some more content is left.
Plus Z.
We have,
Okay, let me tell you why. Because
okay, I will skip the batch normalization today. I will do it tomorrow. Okay, along with the implementation. Today we'll be just seeing the last two topics. Okay, the data dropout and the data augmentation.
It's a predefined command. Bash. Okay, and
okay. So before that, this one page. These are basically the techniques to improve the model. Okay. Now these are not specific to the CNN, like except this data augmentation part. The batch normalization and the dropout, they can be applied to your artificial neural network also. Okay, or any other neural network also. These are not specific to your CNN.
Okay.
Okay.
This is why don't use control.
They are basically the techniques for regularization. So I hope you remember the regularization. These are used to avoid the overfitting case and to optimize my model performance better. Okay. So the first one, that is the dropout. Okay. So before that, I will ask one question. How many of you remember the ensemble method?
Basically, what control plus
what does ensemble method?
We will learn later on. It is exactly when I learned this.
Yeah, anybody want to explain what is ensemble method?
Yeah, so like different methods to like ensemble the results from different models.
We combine weak learners, no?
Weak learners to arrive at the.
Okay. So the main idea for the ensemble was that like instead of using just one model, we create multiple models. Okay. And then we will basically aggregate the output of them to get the final prediction.
Using either voting or on different methods.
Yeah. Okay. So why can't we do this same thing on the neural network? What do you think will be the main problem there?
Computation. Too much of computation.
Very good. Okay. In training one neural network itself, if you train a deep neural network, by deep we mean we have multiple hidden layers, and in each layer we have many neurons. In training one, it takes a lot of computation power. If you are just going to replicate the same idea of ensemble in the neural network, then it's going to increase computation cost. Okay. So the workaround of that is kind of like a dropout. Okay. So in dropout, what we do at the time of training,
Now pay attention.
I should make a duplicate of this slide.
My cursor here. Okay. Now when I press I, okay, I'm pressing I just press small I.
Okay.
Okay, and
so what we do is
bottom,
we will randomly select some of the neurons.
Now I am in the insert.
Okay. And by some probability P.
Press number 1. See where it will be printed. 1. Where did it get printed? It
P,
got printed.
We will drop some of the neurons.
N was earlier.
Okay. So as this example shown here, this dotted one I am showing. Okay. It's dotted because I have dropped it. Okay. Or I have zeroed its output. So it's, there will be no output that's going to flow from there. That's why all of these outputs are also dotted. Okay. In this next layer, let's suppose I will drop this. Okay. Of course, I'm not going to choose it in each layer. We set some probability, and by that probability, each of these neurons will have the probability that by some P probability, it's going to retain or it's going to get dropped. Okay, if P is the probability that it will drop, then 1 minus P is the probability that it will retain or it will stay in the network. Okay, so in this example, there are only 2 neurons that are getting dropped. Yeah.
This is insert mode.
Okay.
Okay, and you can enter
and then I am just going to do the feed forward on this part, one nut. Okay, and do the backward propagation to update only those weights which took part in the feed forward calculation, as these weights did not take part in the feed forward calculation because this weight, this neuron and this neuron was dropped. So while doing the backward propagation, I'm not going to update these weights. Okay, because they were dropped.
This is what is insert and
yeah, now Shubham.
Okay, you should.
So what do you mean by some probability we will retain the things like the steps?
So each of these neurons in these layers, okay, they have the probability P. It's uniform for all the neurons. That by some probability, let's say 0.5. I am going to drop the neurons in this layer. Okay, so if let's say like 0.5, that means half of the neuron in this layer can be dropped. Okay, so 1 neuron I have dropped. So half of the neuron in the next layer can be dropped. So I have dropped 1 here. Next again. Okay.
And now I'm
so that value is being decided as a hyperparameter.
Yeah, it's again a hyperparameter. What probability you want to choose.
Now I'm going to type 5,
okay.
6, 7.
So
5, 6, 7.
What this network after dropping the neurons, it's called a thin network. We call it as a thin network because it has a less number of neurons. Okay. Now, in every turn, as I said, we will do the feed forward calculation, and in the backward pass, we are only going to update the weights of those neurons which took participate in the feed forward calculation. As this neuron was dropped, so we are not going to update this weights because they did not take part in the feed forward calculation. Okay, only these weights that took part, these weights here. Okay, I should blur this also. I think I forgot to it, but this arrow should also be blurred. Dotted one.
Now let me. Okay, now you can see that I am.
Okay.
Like it's not a dense pack.
Yeah, it should not be dense.
Not fully connected.
Yeah, it should not be dense here. It should be dotted because this neuron is dropped. I will fix this error. Okay, in the final part.
And
I'm just
then
asking.
one more weight is also there, which
ANN
should be
will
blurred, right?
Which one?
Now I can write
The last one, the bottommost.
You mean this one?
Yes.
Yeah, this one should also be there. Yeah.
Let's make it down.
Nice.
Okay, and you can see
do
I
it.
can press enter also. Okay, I can type a new number. I can type.
Sir, is it not possible to deactivate instead of dropping?
And I can move.
Yeah, see, the main idea is we will do the masking.
Also using the delete key also.
Okay, that's like for the normal understanding point of view, you can think of them like we are dropping them, but it's not going to actually get dropped. We are just doing the masking. That
Okay, sir.
there will be no flow from this side further on. It's like the output of this neuron will be 0 always. Okay.
Okay, so sir, is it possible for you to move little bit? I mean, because there is no background noise. I think there's some other.
Okay, 1 minute.
The person is teaching TDS.
Serious, I thought it's system command.
Yeah, it looks
Yeah, sorry,
system commands.
System command. Yeah,
It's
system
ST
command.
only.
Sorry. Yeah.
1 minute. Yeah, it was system commands only. They also have session from 9 to 11. Yeah, is it okay now?
Very little space for you people to sit in the campus.
No, it's like we have
Mostly
only
we
one.
are hearing some other classes in the background.
It's like we have the enough space, but it's like how big they can give, right?
We need to do some padding basically on the space.
Yeah. And that is on the case when like some of the TAs do not take session from the office, they take session from the hostel itself.
So that's dropout.
Yeah, that's dropout. Okay, nice. We are using the concept that we are learning into the real life. Okay. Yeah. Okay. So
now we drop out and do what?
Yeah, I am coming to that. So one thing that it is not necessary that in each forward or backward pass, only this neuron will get dropped. As in the first pass, it can happen that this neuron get dropped. But in the next pass, it can happen that this neuron can retain and this neuron can drop. Okay. In that case, what will happen? These weights will not get updated, but these weights will get updated. Okay. So first of all, is it clear till now?
So it's like constant switching out here and there.
Yeah, like it's just a probability. Some neurons will be there, some neurons will not be there. It's not necessary to be constant switch out. Okay, it's just a probabilistic way.
Probability that it will switch out somewhere.
Yeah, some neurons will be active, some neurons will not be. Now, if I like take some more, then it can happen that these two are not there in the first. Again, it can also happen that in the next part, in the next pass also these two are not there. There's not necessarily that there will be a switch out. Okay, as it is all depends upon the probability.
Okay.
So will it affect the updates?
Yeah, of course it will affect
Switching
the updates because the neurons which got dropped or which got masked basically, okay, the weights corresponding to them will not get updated. Okay, just like in the first case, these weights will not get updated. But of course, in it can happen that in the next pass, this neuron does not get dropped. Then in that case, its weight get updated. Okay.
So, but it will create a error type things. Like it will not behave properly.
It will behave properly. The idea behind this is we are not just letting our neural network to depend only on few of the neurons. Okay, we are
we are running many times the same thing.
Yeah.
By selecting one thing and by dropping another for every time.
Yeah. So what it usually do is sometimes it can happen that your output is dependent upon only few of the neurons. Okay. So because of this dropping scenario, now we are forcing other neurons also to learn more abstract features or robust features. Okay. Because if let's suppose this neuron is what dominating here to predict the output. Okay. And if we drop it, then it will force the other neurons in this layer to learn the features in the training process. Okay. So that's the main idea behind dropout. Okay, we drop few of the neurons in each layer by some probability p. Okay, the main idea behind is that it will allow other neurons or other neurons in the layer to capture more robust and abstract feature. Okay. Yeah. So, any doubts here?
We've learned, but when you put them all together, how it will be the performance?
See, every time it will be like a different kind. So it's that's why I asked about this thing in the starting, the ensemble part. Because in the ensemble, what we do, we create different models. Okay, here also similar thing is happening, right? Because if you just remove this, it's kind of like a different neural network, right? And in every pass, you will get a different structure. So you are creating kind of a replica of the ensemble methods every time. Okay. The only purpose is to improve performance. Yes, it's a regularization method. Just like your L1, L2 regularization method is there. Okay, it's a regularization technique. Okay.
I have a doubt. If you said no, that neurons, if the neurons are dropped, then how the other neurons are forced to learn? No? If the neurons are dropped, which are having much information, then our classification will be not good. No.
Yeah. So if the classification is not good, then the weights will be updated in such a way for these neurons such that it is able to correctly classify in the back propagation.
Okay.
Okay.
Okay. Okay.
Yeah.
These, whatever we are, the concepts, what you are teaching us today, Pulkit, tomorrow you will demonstrate?
Yes.
Yourself or someone else?
I will do it. Tomorrow session also I will going to take. Like I'm not available on week 4 time. Okay, so the next week I'm not available. That's why this week both the sessions I will be taking.
And
next,
your coding session is like we can code along, or how is it?
like I will be coding. So if you want to code with me, you can code. Your wish.
How is your flow? That's most important, right?
That you can see it later, because for now I have one more topic. Let's first discuss it. Okay.
Okay.
Or else you can watch my MLP sessions.
You can easily follow along. He's really good in that. We have done his recent MLP sessions.
Yes. Yes. Yeah.
So usually he starts from scratch. I mean, he start writing code from scratch.
Thank you. Okay, now few of the points about dropout. First thing, I'm going to write it in the next one. Dropout is only applied at the time of training. So by training, we means that the neurons that we are dropping, okay, this thing only happen at the training time. Okay. At the inference. Okay, or the testing. We use all neurons. Okay. So at the testing time, you are not going to drop any neuron. You are going to contain all the neurons that you had in the initial part. Okay.
You have already downloaded WSL, no?
Third point. Now, in the training time, of course, we have created different version of the neural networks. Okay, by dropping different neurons in each layer. Okay. Now, if you're trying to replicate the same thing that we were doing in the case of ensemble method, what we were doing at that time, we were aggregating the output of these. Okay, but again, the same thing is happening that we had in the initial part, that the computation cost. If we store each of these different network, okay, then again the computation cost will blow up. Okay, so what we do is we do the scaling of our output of the neuron. Now, there are two variants of dropout that you are going to see. Okay. In the one variant that is there in the degree level DL course. Okay. Yeah, that is the Mitesh lectures. Okay. In which we do the scaling at inference time. Inference time is basically testing time. And with what factor we do the scale? Scale by probability P.
SSH is kind of
okay.
the most important thing.
So I should use 1 minus P here. Okay, because I am considering that P is the probability that it will drop. Okay, so 1 minus P is the probability that it will retain. Now the reason why we used scaling with 1 minus P, because at the training time, this neuron is only active at 1 minus p probability time, right? So that's why at the inference time or at the testing time, we scale the output of this neuron. Okay, so let's suppose after doing the activation, you got the output as something like 0.4. Okay, and your probability p is 0.2, then 1 minus p is 0.8. So you will scale this output by 0.8 into 0.4, 0.32. Okay, that will be the output that will feed into this next neuron. Okay, this was one variant, but in our course, okay, we had another variant that is scaling at the training time. Okay, and basically that's the variant, this variant, scaling at the training time. That's the same variant that is implemented in the PyTorch. Okay, and in the TensorFlow 2. Okay, in the TensorFlow 1, the first variant was there, scaling at the inference time. But in the TensorFlow 2, we had the scaling at the training time. And in the PyTorch, current PyTorch version also used the scaling at the training time. Okay, and in the lecture also, sir is went with this. Okay, but if you just want to remember, you can remember this also, because in the future you will be seeing this variant in the degree level DL. So that's why I mentioned it here. Okay, but how the scaling at the training time happen? We basically scale the output by 1 minus p, x divided by 1 minus p. Okay, so this is how we do the scaling for the training one. Okay, so if I take an example, we are doing the training, some neurons are dropped, the remaining neurons, okay, their output we will scale it by 1 minus p factor. So it's kind of like if you are using the probability for 0.5, okay, and the probability that half of the neuron will get dropped, and for the remaining neurons, what will happen if you are going to scale it by 1 minus p? It's like 1 upon 2. Okay, it will be like double the output of those neurons, right? Okay, so basically the expected value if you are going to capture. Okay,
what is the numerator you have written? X or which what numerator?
Numerator x. Okay, x is basically this output of this neuron. Okay, so if I try to find that, so what basically sir has mentioned that why we this scaling of 1 by 1 minus p makes sense is basically if you find the expectation of output of each of these neurons. Okay, there is a probability that by some probability this neuron output or this neuron will be dropped. So in that case, the output of the neuron will be 0, because by dropping means we are setting the output of this neuron to be 0. And there's a 1 minus p probability that the neuron will be there. If the neuron will be there, then we will scale the output of that neuron with 1 by 1 minus p. Okay, and that's how you calculate the expectation, right? So it will still comes out to be the same x. Okay, so the overall things will remain same if you scale it by 1 upon 1 minus p. Okay, so is it clear?
Yes, sir.
Yeah. So another wording for the dropout is also masking. Okay, so that, as I said, that dropout is only applied at the time of training. Okay, another wording for the dropout is like masking, that you are masking the output of these neurons. You are not allowing the network to flow from this direction. So if the option is something like in the question, like masking is only applied at the time of training, that is correct, because that's the same wording here. Okay, while in
So the difference then is, in case of dropping, you drop the node, all the associated edges also get dropped.
Yeah, because no weights will get flowed from there.
Right, but in case of masking, you kind of the edges are still there, right? So that's a big difference.
Yeah, you can think of it like that. But still it's the output will be the same in that case, because you will not allow the network to flow from that direction, because the output will get zeroed from there.
Got it. So
This is
there's no
just for the
computational
visual
shading.
representation, like we are dropping it.
So from a computational perspective, the dropping out actually saves time. For masking, I'm doing all the computation, then making it zero.
See, in the reality, we are not dropping it. It's beyond out. It's the masking only. Okay.
Correct.
Okay. Because if we drop it, then the structure every time will be different, so it will be hard to calculate. So we do the masking. Okay. So it will be like you will create a feature map kind of, or like a masking vector. So masking vector is like this is the two neurons are there. So I can create a vector like 1 0. 1 0, what does it represent? 1 means the first neuron will retain. 0 means the second neuron will get dropped, or its output will not flow. Okay, so this type of masking vector will be there.
So you do a dot product between the output of that layer versus the masking vector.
Yeah. Okay.
So I think I have got a good idea to visualize this dropout things. Like it will be like the thing which we see in the Diwali lights. It will twerk.
Yeah.
Like
Kind of
that
like
thing is there.
yeah.
Yeah.
Every time, but again that light follows a pattern. Okay, but here it's a probabilistic way. It will not follow any pattern. Okay. Like it's not necessary that every time it will switch from this neuron to this neuron in the case of dropping. Okay, that will not happen. Yeah. So yep. Let's conclude the dropout. Dropout is only applied at training time. At inference, you will contain or take all the neurons. Okay. Then you will do the scaling. Okay. Now again, just let me make sure it once again. This part was in the degree level DL. Okay. So in the exam, if it comes that in which time you apply the scaling, you should take the training time, not the testing time. Okay. So maybe I will remove it for now. Okay. Yeah. And we do not scale it at the test time if we are already scaling at the training time. So let's move on to the final, like not final, there is one more batch normalization that we will do it tomorrow. But the data augmentation. Okay, it's if you have done MLP last time, that in that week 8 image classification also we have studied this, right? Data augmentation. It's the same factor that for your original image, like for this cat image, you can do the vertical flipping or the horizontal flipping, some degree rotation of the image. You can blur the image, you can brighten the image, you can add some noise in the pixel, you can make it darker, grayscale, you can crop some part of it, as long as the final output that you want. That is, if it is like a classification problem between whether it's a dog image or the cat image, as long as the label is not changing, you can do these type of different operation on the images to create more data for your network. Okay, as these data that you are creating, the new data is coming free for you, right? Because it's just coming from the original image or original data only. So as doing this operation on this cat image does not change the label, because a cat is a still cat if I do the horizontal flipping of this image or the vertical. Okay, whether it's a grayscale or it's a darker, brighter, noise added image. Okay, it is still a cat. That's why the label will not change, and that's why it is good for your network. But we have to be careful. 1 minute, Kailash. Okay. We have to be careful while doing the data augmentation, because sometimes while doing these techniques, it can change the label. For example, of your classical MNIST dataset, which contains the handwritten digits. Okay. If you do the vertical rotation of this 6, it can become 9. Okay. So you have to be careful while applying the data augmentation, that whether it will going to change the label or not. Yes, Kailash.
Yeah, sir, in sense of ML, These all images are different now.
Yeah, these all images are different because the pixel values will be different in the case. Okay. Yes, Shubham.
So here, like, we are creating a multiple copy of the original image in different versions. Like, can we say that we are doing the filtering parts, like darker part and the grayscale part and the cropping part? The last three.
Yeah, kind of it's a filter. Okay,
Yeah.
because if you apply certain kind of filter, then you will get these outputs.
Yeah, that's, I think it comes under the augmentation only.
Yeah. Okay. If you use that as an input to the network, then yes. Okay. But of course, these parts like horizontal, vertical flipping, that can be done using the pillow library methods. Yes, Priyanshu.
Sir, the last one when we see this cropped image. So is it something to do with padding? I mean, let's say we have put inappropriate filter, that's why it has got cropped, and we can put some padding to
No, this
retain
is
the.
not related to padding. It's just how you normally crop an image in your phone, right?
Sir, under the hood, what is happening? And when we crop, so are we, I mean, removing some feature because we have cropped, right? So like half of the ear and face, it's gone. So, but underlying mechanics of how it works when we crop. So is it because it looks like it is also based on CNN?
Yeah, some task will be there, but I'm not sure what happens in the under the hood for this
Okay,
task.
sir, no worries. I will check.
Okay, so data augmentation is simple technique. Only thing we have to be careful that by mistake we do not change the label while doing any kind of techniques. So like an example that I gave, if you have an classical MNIST data set, you cannot apply the vertical flipping in that case because it can change the label. Yeah, so with that, only part that is remaining from the week 3 is the batch normalization that we'll do it tomorrow, followed by a demonstration of the convolution neural network on the fashion MNIST dataset. Okay. Yeah. So anyone has any doubts in whatever we did today? Okay.
This
Thank you all.
technique is only for the images, is it? CNN.
Yeah, CNN is mostly used for the images only.
Videos or videos.
Yeah, videos is basically the sequence of image. Okay. Sorry. Videos are basically the
What
sequence
will
of
happen
image.
if I use this instead of ANN?
You use CNN on some other
ANN
task.
has a purpose, right? Where
Yeah.
we studied ANN for a certain purpose. Why if we use CNN, what will happen?
See, each network that we are studying here has its own purpose. So NN can be used for your simple tabular structure data. Okay, of course, other classical ML models can also be used, but NN can give much better performance if you train it properly. Now the CNN is basically desirable for the images. After week 4, in the week 5.
Don't take it in the same sense. Like in the ANN, why we are not putting a filter and then doing? Because this filter is like a lens. I just scan it on an image. I can do that on the any other data set also, right? Like a filter. We can make a filter for any type of data, right?
Okay, but then how you are going to define the entire structure if you are doing the filter case?
A filter by itself is a hyperparameter. That is this one has to take care.
See, the filter and its mechanism, the convolution operation that's defined in the CNN, has its meaning, right? You are sliding the filter throughout the image, and then using that you are getting a feature map. And in the case of ANN, if you are going to take a filter, ANN takes a 1D case. Okay, so you can take a 1D filter, but still one of the problem that the destruction of the spatial features will be there because you have to flatten the image. Okay, And if you are flattening, again the number of parameters will blow up.
Flattened, right? ANN will not be having this problem, right?
ANN will be having.
Normal, it will be having feature, but not to this extent. This like 224 and 224 will not be there. There will be 50 features or something like that will be there, or 10 features. Flattening problem will not be there for ANN problems, right?
Okay, you want to use ANN for a simple tabular data structure, but you want to use filters there. You are saying like that.
Yes. What will happen?
Okay, so see the
maybe
simple
we can discuss tomorrow also this one.
Yeah, I can give one-liner example, one-line explanation here that ANN basically tried to capture, make a dense connection. Okay, while CNN, if you see, it's not a dense connection because it's not looking at all the features at once while creating the output. While for the ANN, it uses for all the features that you have at once to predict the output. Okay, so I think you can.
It causes an overfitting issue when we use it with images. That's what you are trying to indicate?
No, not the overfitting case in the ANN. It's basically it's not able to perform well. You will not get good result in the case of ANN. Okay.
So for tomorrow, like you will do the coding part. So, like what things to be seen, like as a prerequisite to join that?
For that, of course, you should know how you create a custom network. So by now, because we have already seen it 2 times in 2 weeks. Okay, so that part I'm not going to touch upon it further. Okay, yeah, of course, I'm going to touch upon how you create a convolution layer and the max pooling layer. Okay, but we'll first start with how you create a convolution and the pooling layer without using PyTorch, like using your simple Python or NumPy, how you can create that. Following that, we will do the visualization, a little bit visualization, okay, using Matplotlib. After that, we will load the FreshNMN dataset and create a simple CNN structure, okay, and then we'll follow up that. So that's the thing that we are going to do tomorrow. So you should have a basic understanding of the NumPy and the torch operations and how you create a custom networks.
Okay, sir. Fine, sir. Thank you, sir.
And like simple Matplotlib, how you plot the images. If you want, you can explore the imshow function in the Matplotlib. Okay, plt.imshow is what we are going to use to plot an image using Matplot. And some of the major things that we are going to use to plot multiple images together is plt.subplot.
So these things we have already seen in MLP.
Yeah, same things that's going to be there for the plotting purpose, nothing changed.
This these videos are too many, so the in the course content there is this lecture slide, right? Lecture slide covers all the part of the videos.
Lecture slides only cover the theoretical.
Lecture slide.
Lecture slides only cover the theoretical part. Okay. So for the demonstration part, you can either look at the collab that you have in the
if I see the lecture slide and the collab notebook in conjunction, will I cover all the videos? Because the videos are like 4 hours per week or 4.5 hours per week, like that.
Good night, Pranshu. Yes, if you cover that, that's the thing that covered in the lecture.
Okay, lecture slide and collab covers everything of the.
Yeah, but we have the like mixed collab for week 3 and week 4. Okay, and the slides is also combined. So you should know like where to stop reading the slides. Good night, Mona Lisa. Okay.
Thank you. Thank you very much.
Yeah. Okay. Welcome everyone. Thank you all for joining.
Just one thing for NPP, NPPE 1, like and 2. So do we have like kind of papers, or like it would be some questions to solve?
so far we do not have any idea how the NPP is going to get conducted. So wait until that time comes. At that time, you will be notified how the structure will be there. Okay, whether it will be like similar to the MLP or it will be like Kaggle thing that is there in the MLP.
Okay.
So most likely it can be like a Kaggle assignment, but let's see.
Oh, thank you.
Okay.